to Athena, who is going to introduce our speaker for today and take us through the webinar. Over to you, Athena.
Hello, Peter. Thank you very much.
I can activate video.
Yes, if you could activate my video, Peter. Thank you very much. Now I'm on. Welcome, everyone. Good evening, good morning, good afternoon, wherever you are joining us. It's my pleasure to introduce our speaker today, David Gull from the University of Haifa. And he'll be speaking, his title of his presentation is Between Practicality of Windward Sailing and Predicting the Weather, the Human Factor in Ancient Sailing Mobility. The point of departure for this article, as I'm sure he will tell you, is an article written by David and his co-authors Hada Saroni and Deborah Zwickl. It's called Windward Sailing and Antiquity, The Elephant in the Room, which was recently published, and it's open access on IJNA website. In late April it was published, and it will be part of volume 52.1 coming out in June. David received his first degree in computer science at the Interdisciplinary Center Herzliya and recently completed a second and third degrees in Maritime Civilizations at the University of Haifa in Israel. David has been sailing the Mediterranean waters the last 35 years and is also a keen self-educated marine meteorologist supporting the sailing community. And currently David teaches a master's program course, Seamanship and Sailing Mobility and Antiquity, and is conducting several postdoctoral research projects, both at the University of Haifa. So David, I hand it over to you.
Thank you, Athena. Thank you for a very kind introduction. And thank you for choosing my article as the subject of the webinar number 6 of the IJNA. The subject today is the human factor in ancient sailing mobility. Let's see, do I get the next slide? Yes. But the occasion, as Athena mentioned, is the publication of a recent article which deals mainly with windward sailing, both the technological capability of ships and the impact of the human mariners on windward sailing. So today I'll expand on that and give a broader presentation, which will include a small chat on the need to derive sailing mobility and the involved actors. We will discuss the elephant in the room and see if we can perhaps reduce its size a bit. Discuss the practicality of windward sailing, and then look at the broader aspects of sailing mobility and the metrics that are available once the human factor or the ancient mariner is incorporated in the modeling. And finally, a few words on the capability of predicting the weather, because it's fine that we can measure mobility. The question is, would the ancient mariner able to judge when was a good time to go? We know as an afterfact when it was a good time to sail and when it wasn't. The ancient mariner needed to predict that. The sea is not a frictionless surface. Different passages are either easier or more difficult to sail. It's not an issue of deciding want to sail from point A to B, point the ship in that direction, trim the sail, and go. There are seasons, there are contrary winds, there are supporting winds, there are favorable winds, and there are storms. Looking at evidence, while there's plenty evidence on the existence of maritime links, there's very little evidence on how these links actually functioned. So researchers had a look at alternate routes, and the main one that has been followed, especially in the last decade and perhaps a bit more, is attempts to derive potential sailing mobility by modeling its three primary actors. namely the ships, the wind, and the mariners. Unfortunately, on all counts, there are significant challenges. The mariners in some of the studies are simply just not included. There's no modeling of mariners at all. Well, we will see in this presentation, it's a bit of a spoiler, that they have quite a dominant effect on some of the aspects of sailing. The wind too is very difficult to handle in modeling sailing. There's a tendency to use average winds, and average winds hide a lot of the data that could be important in understanding where are the opportunities or the windows of opportunity to find favorable winds. And it's simply the stating that an average wind represents, or the average sailing can be derived from the average wind, completely forgets the fact that the mariners would pick and choose when they wanted to sail, when the conditions were suitable, and when they wouldn't sail. Fear is definitely a big factor here. Thank you, Arthur, for pointing that out. And then the ships. The ships are definitely perhaps the biggest problem in deriving sailing mobility, because there's a very broad discord in what is the performance or the windward performance of a Greek or Roman ship. And just to step forward on that point, it's possible to say there's about 3 schools of thought on windward sailing. The first school of thought, which is shown by A in the diagram here, I'll just put on a pointer. Shown in diagram A shows a relatively smaller no sailing sector. So the school of thought that sees this as the performance of ships claims that there is practical windward sailing. In other words, it is possible to sail to a destination that is in the eye of the wind. Of course, it requires tacking, and the average passage speed would be lower, but it is practical to sail to windward. The second school of thought says, no, the ships have some windward capability, rather small, perhaps enough to crawl away from a lee shore, but not enough to complete a passage from start to end with contrary winds. Third school of thought says, no, the ships were completely downwind ships with no upwind capability. At best, it was possible to sail 90 degrees to the wind, approximately. So digging deeper was definitely warranted on this particular count. And we did conduct, and it's detailed in the recent article, a reassessment of Mediterranean ships' windward capabilities. First thing we did was to look at the scholarly sources. Who wrote what about windward sailing, and what can we learn from that? Second, we revisited the theory of windward sailing. There is a theory. And third, we looked at the experimental archaeology sailings of reconstructed and replica ships. Our literary review started with James Smith, who in 1880 published a dissertation on the voyage and shipwreck of St. Paul. And he does claim some performance, give some idea what he claims to be the performance of the ships. But more interesting, I found comments of his in the introduction. The first comment regards the peculiarities of ancient navigation, where he said, there is not a department of classical antiquity about which we are so much in the dark. I've not met any modern author on the subject who has not left it more obscure than he found it. Quite encouraging. Then he continues and says, there's scarcely a single nautical term in the narrative which is correctly rendered. And even when one is, the reader has no certainty that the meaning is the right one, for he will rarely find 2 commentators agreed in opinion respecting it. So on that positive note, we continued our survey of texts. We did a waterfall chronologically starting at 1880 and ending in 2022 of all the main publications that have something to say about windward sailing. And of course, who is referring to who. So we can see the arrows, dotted arrows pointing upward in the map. And definitely we can see there's suppliers of information on windward sailing, and they're consumers of windward sailing information. A little bit of concern is that in the last 10 years or so, many of the consumers are running models and doing inputs to network analysis. So they're creating new data on previous data. The three most cited suppliers, as I call them, are first of all Mikhael II, who in 1990 published a paper on it, which was taken mainly for the logbook of the Kyrenia II, analysis of the experimental voyages of Kyrenia II. Kaysen in 95, which is actually the second edition of his book, Ships and Seamanship in the Ancient World, has a chapter on ship's speed, and he's widely quoted. And then more recently, Julian Whitewright published The Potential Performance of Ancient Mediterranean Sailing Rigs, and he's very widely used as a source for windward sailing. Let's take a peek at Kaysen's method to derive ship speed. He quite openly said, I have no idea what the performance of an ancient ship is, and there's no evidence on it. But what he could take, and he said he could take, was historic non-stop passages with given durations. In other words, there are plenty mentions of sailings, which is it's known that there was no intermediate stop, and the duration is known. And he listed those that are conducted with favorable wind and those conducted with unfavorable winds. Calculated the average speed and then concluded that ships could sail 4 to 6 knots with the wind or downwind and 2 to 2.5 knots against the wind. It was quite clear on what unfavorable foul winds meant, and those that blow from some point ahead of the ship. So definitely an unfavorable wind is considered a contrary wind. He also claimed or asserted that ships could probably point no closer to the wind than 7 points. That equates to 78.75 of a degree. And said when his destination, or the mariner's destination, lay well to windward, he resorted to tacking. So if we take a closer look, these two, the conclusion of 2 to 2.5 knots and the assertion that they sailed no closer than 78 degrees to the wind, are in somewhat contradiction, because we need to look at what boat speed would result in 2.5 knots effectively windward. Cosine of 78 degrees is about 1/5. So it means in order to get 2.5 knots windward, effectively windward, the ship's speed would need to be between 10 and 12 knots. The average wind in the Mediterranean is only 10 knots, so there is a problem here. What we decided to look at is whether the passages that were listed as conducted with unfavorable winds, were they actually conducted in contrary winds, or could they have been conducted in favorable winds in the other direction? So this is the list of, I think, 10 sailings that Lionel Kaysen gave us. 4 of them are related to Mark the Deacon and the travels of the Bishop of Gaza. And we took the one from, we took all of them actually, but I'll show you the one from Caesarea to Rhodes, where the date is exactly known on which he sailed. At the end of last week of September and the beginning of October, he arrived in Rhodes. in the historic sailing, it was 10 days at 1.8 knots. Now we have done mobility measures on this route, and it already coincides. We show the medium passage duration that we have is 8 days. The medium passage VMG, velocity made good, is 2.2 knots, but the 10 days and 1.8 fall within the spread of the data, within the spread. And then we find that the destination on sailings in October is on an average no more than 14% in the no sail sector. So it's not really an upwind passage. There were some portions of the passage where the destination would be a little bit to windward, but only slightly to windward. And 45% of the time, the ships were reaching or sailing with downwind points of sail. We looked at the rest of the sailings except 2, and we came to the same conclusion that they all could have been sailed with favorable winds in the other direction. Maybe not as favorable as the prevailing winds, which are more steady and provide a higher average speed, but definitely could have been conducted not contrary to the wind. Julian Whitewright also established that ships could do a maximum of 2 knots velocity made good to windward, very specifically on windward. And how he did that is he took Cayson's list and slightly modified it, showed that the average here is 2 knots, but that's passage VMG, the average speed of the passage. He then compared this to the results of reconstructed ship trials, most of them Viking trials, and said, oh, these are somewhat around about 1.5, 1.8 knots, some of them perhaps 2, and that tallies with 2 knots passage VMG, and he concluded therefore that it was 2 knots. The small problems here is that it's not necessarily an apples to apples comparison, except in the one case when the destination is in the eye of the wind throughout the passage. Then passage VMG and windward VMG would be exactly the same. Whitewright justified his system by saying that the concept of velocity made good is central, and it allows to compare 2 ships independent of factors, which is not quite exact because the velocity made good windward depends on the ship's speed, and the ship's speed depends on the wind speed. So a Mediterranean ship capable of 73 degrees effectively windward, and a Viking ship, the Viking ship, if it was tested in 24 knots, it would generate almost 2 knots windward. But if a Mediterranean ship would be tested with 2.5 knots wind speed, it would only generate 1/2 a knot, but they would both have equal capability in sailing to windward. The most important thing about Whitewright's work is his conclusions and his summary, in which he said, although he's shown the maximum possible speeds that could be achieved windward, if the conditions are right, and said then that in the majority of cases, it's unlikely that such performance would have encouraged ancient mariners to set out on a voyage against the wind. The practice of waiting for a suitable wind direction must have been the norm, which is an excellent caveat to his work. Unfortunately, in our mapping of the literature, we didn't find one work that quoted this conclusion and this caveat. Michael Katsev gave a 1-point measurement of windward sailing, or so-called windward sailing, with the Kyrenia II in its voyage between Greece to Cyprus and back. and stated, later in the afternoon, the wind shifted to the southwest, and during a 2-hour period around sunset, Carina 2 sailed at 50 to 60 degrees off the eye of a 2 Beaufort wind, close hauled, port tack, making over 2 knots speed, evidence of her ability to sail effectively into the wind. We know from Glavkos Cariolo, who also to publish a paper, that all readings of the wind in this trip were taken by the handheld compass and were all measurements of the apparent wind. So there is a big difference between heading into the apparent wind, 50 or 60 degrees, and the course made good to the true wind, which could be 25 to 30 degrees more. Because there is a need to look at the difference between the true wind and the apparent wind, which depend on the boat's speed or the ratio of the boat's speed and the true wind speed. And we also need to look at the leeway, which probably starts at 10 degrees at best when ships like these are close hauled, and might be as large as 30 degrees. So it's an issue of using the right terms and being very careful what terms were stated before using the 60 degrees as an effective degree that angle that could be sailed to the true wind. Coming now to the theory of sailing. There are some general resources, excellent ones and quite recent too, which give a lot of explanations on the windward sailing of ships and how we can calculate it. In the context of nautical archaeology, Colin Palmer in 2009 published Windward Sailing Capabilities of Ancient Vessels, which is an excellent resource. And central to Palmer's publication is the Better Theorem. We won't go into all the intricacies of the Better Theorem, but I'll just mention that it states that when sailing close haul to the wind, the force of the sail applies a sideways force to the vessel. You can always picture that in the sail here, which is trimmed for windward sailing. The wind is maybe pushing more on the ship towards the left than it is propelling it forward. To counter that, the hull creates lift in the opposite direction, balancing the sail's sideway force. And that lift is created by inducing leeway. The more efficient the sail or the hull or both of them, the vessel can then sail more effectively closer to the wind. And this can be calculated. But the main question is, how efficient is my sail and my hull, which is something that can't really be measured accurately in a full-scale ship in regular sea conditions. So practical measurements require a wind tunnel for the sail and a tow tank for the hull. And any measured efficiency of the sail or the hull are expressed in terms of lift to drag ratio. Is it the sail generating more lift in the forward direction than it is drag in the sideways or the backwards direction? Now, Palmer came to the rescue on this, and he provided in his article a range of measures from tests on representative models. He also showed how much these measures, the degradation of them by various factors. For instance, is the hull smooth or rough? Is there a lot of biological fouling or not? Are there wind waves? How high are the waves? How frequent are the waves? All these reduce the efficiency of the hull. The sail's efficiency is reduced by the oscillation of the ship, its pitching and rolling, and also by how well was the sail tanned? Is it permeable? Is there air coming through it? So what Palmer gave us a range, and he said we can see that a hull of a merchant ship in the Greek or Roman period would have a lift over drag of between 1 and 1.9, and the sail would be between 1 and 1.5. So we're going to look at the horizontal and the vertical ranges and their intersection. So in other words, the windward capability is going to be in this, which shows the dotted dashed line is 100 degrees, solid line 90 degrees, dotted 80 degrees, and dot dash would be 70 degrees. One other caveat about this system of the Bethe theorem is that the Bethe theorem always errs on the optimistic side. It takes the best hull lift over drag that we can achieve, and the best sail lift over drag that we can achieve with the ship. But in sailing, if we trim ourselves to get the best sail lift over drag, we're not necessarily going to be at the same point that gives us the best hull lift over drag. And if we adjust to get the best lift out of the hull, we're probably not going to get the best lift over drag on the sail. So this is as good as it can possibly get. Experimental sailings. One thing that reading all the publications on experimental sailings is something that has to be noticed, and is quite clear that both authors and readers are perfectly human with all the weaknesses of human nature. Authors tend to highlight the best achieved values of windward sailing. It's always in a standout box. The publishers also help on this. And the readers attempt to adopt the highlighted values and to ignore reservations and caveats, which are usually always there. Second problem with experimental sailings is that tests in sheltered waters are not representative of real-life open sea conditions. And we can learn that especially leeway grows very rapidly as the waves increase. And it's very difficult to get reliable onboard measurements. And the best and really only reliable measurements are from an external observer, such as the GPS satellites and the tracks that they can produce for us. They can provide an accurate reconstruction of the actual sailings. Here I've brought a sample of 3 different situations with the Ma'agan Mikhael II ship in the recent year or so. In force 2 winds of only 7 knots, we see that the ship was capable of between 71 and 73 degrees to the wind, half of the tacking angles that are showing here. And the ship was gaining windward, even though it was losing on the jibes, on every wearing. It gained windward. The wind increasing to force 3, giving it about 10 knots speed. The ship was then capable of only 81.5 degrees effectively sailing to windward. And any windward height that was gained, ground that was gained, was lost in the wearing. So the ship basically stayed at the same point, even though we were sailing to windward on each tack. With the wind increasing to force 4, that's 12 to 13 knots, and white caps all over the sea, and more prominent wind waves, we could hardly get 180 degrees tacking angle, which is about 90 degrees to the wind. And in general, this whole exercise lost height to the wind. That performance aside, we need now to look at the human factor in windward sailing. And we'll bring an example in looking at the practicality of sailing windward from Paphos in Western Cyprus to Rhodes, which is definitely a passage which is normally contrary to the wind, especially throughout the Etesian season, the Meltemi season. Here we have different angles that the ship is capable of sailing windward, and we took the example in the highlighted of the 7 points to the wind, 78 3/4 degree. First problem is our helmsman is very unlikely to keep a perfect route track against the wind, and he will sometimes steer too high, and he'll sometimes steer too low, losing on average 3 degrees, probably 5, which gives us an effective angle of only 81 or 82 degrees. Our ship will be sailing ship speed at 2.5 degrees if we consider that the average wind speed is 10 degrees in the Mediterranean, and that ships do about 25%. These ships would do about 25% of the wind speed when close hauled. So now we're reducing the speed. Our windward effective speed is only about 1/3 of a knot. We're going to definitely lose every time we wear. The ships are not able to turn through the wind. They have to turn the stern to the wind. So over time, we'll probably lose about 10% of that, which means that we can gain about 7 or 8 nautical miles a day to windward. And the bottom line is that on a route from Paphos to Rhodes, it'll take us 29 days, and we'll need to sail 1,725 miles instead of a direct passage of 225 miles. Even ships that are slightly better are still going to be very, very difficult to conduct that passage to windward. So with that in mind, we can come to some conclusions on the issue specifically of windward sailing. The ship's technological windward capabilities are less than generally accepted. In other words, the numbers in literature are generally optimistic, and we can show that they're definitely less. But it's not really important to put an exact number on the above. It really is not important, because the limits of practical windward sailing are significantly more dominant than those of the technological capabilities of the ship. In other words, the human factor overshadows the technological abilities of the ships. And can definitely concur with Whitewright's conclusion that waiting for favorable winds in the needed direction would have been the norm. And a close look at the literature, especially the original sources, really concurs with that as well. We'll now turn to the chapter of the ancient mariners in the more general sense of modeling sailing mobility. Of all the 3 factors, the wind is definitely the most dominant, and there's no doubt in that. But the unique things about Mediterranean winds is the level of recurring variability that are so characteristic to the winds. And even this image here, which is actually taken from a meteorological software, show that at one particular point of time in the south of Cyprus, we can see winds in different directions and forces and very close proximity of one case to another. The opportunities for favorable winds, especially in cases that are contrary to prevailing winds, are probably driven by this variability. Another important thing in modeling is that we needed to establish, if we want to use modern winds for modeling and measuring mobility, we need to prove that ancient winds are equal to modern winds, which is something that was done both looking at the historic proof given by Murray and looking at paleoclimatological studies, which could show that there's been very little change in winds over the last 3,000 years. The methodology, to give it in 30 seconds, is to take a big set of meteorological data, a huge set actually, of billions of records, 15 years in time, with 1 hour spacing between sets. In other words, temporal resolution of 1 hour. We then run sailing simulations on all measured passages to reduce the meteorological data to sailing data. And back to what we're doing is we're data mining favorable winds out of the meteorological data and then seeing how that applies to sailings. Once we have all the sailing data, we can then introduce the human factor and eventually get measures of potential sailing mobility. And I'll discuss how we introduce the human factor in the next few slides. One word on the simulation of the ships was done with the weather routing simulation, which generates isochrones. And the isochrones are developed as the wind changes every hour during the sailing. And of course, every day has its own departure with a different set of wind. In this case, we see sailing from Crete to Leptis Magna in North Africa. And in this particular sailing, the red line shows the least cost path for that particular day, departure day. In all, we did over 1 million, we've done now more than 1.5 million simulations. What do the results look like? Here we can see the same passage from Crete to Leptis Magna in a month of July, one of the months of July that was that, and we can see that most of the lines are more or less smooth and more or less direct from the departure to the destination. Maybe a few of them are a bit more squiggly and not so much in direct lines. So we can see actually visually that the majority of the sailings in this particular month of July were probably good sailings and fairly practical. Whereas if we look at February, we can see that most of the sailings are sailing all over the place, driven by contrary winds. And if we zoom in on what might even look like a straight line, we can see that the simulator has really been tacking the whole way. So we can say that in this month, there are very few passages that would have been reasonable. Now, there's no way to assess 1.5 million passages by just looking at the tracks. So every sailing has a numeric summary, and we can see there what was the ratio between the distance sailed and the direct distance. What was the average passage speed? How often was the destination in the no sail sector? And we can, by setting criteria, we can divide all the sailings into the set of practical or reasonable sailings that a prudent mariner could have sailed, and the other set that would probably be impossible for a reasonable mariner to sail. Once we have the count, if we can say, oh, there are 25 reasonable sailings in July, then there are 25 out of 31 is the mobility, which we can factor normalize to 0 to 1. And February might only show about 5 days or less practical sailing. So what we get from this is new mobility metrics. We no longer use the sole metric of passage speed, and we have now a coefficient of potential mobility, which is the proportion of a month having favorable winds to depart on a practical passage. And we use a coefficient from 0 to 1, just so we can normalize, because July has 31 days and February has 28 days. So in order to have something normalized, we use a fraction from 0 to 1. Another thing that introducing the practical sailing is that we have windows of time when it's not practical to depart on a good sailing. So we have waiting time. So from this method, we can also factor waiting time into passage duration and reflect the true wind costs. Just to give an example of how it looks in one chart, we can see that same passage where we can see for the month of July, there's a bar which shows 0.77 mobility, whereas February would be showing 0.24. We can see this is the blue, the actual net sailing duration, and the green track shows, the green trace shows the time, including waiting time. So if we have such measurements for every possible passage that we might find is part of a historic context that we'd like to examine, we have a set now of metrics that we can apply to a group of passages or a set of passages that have some meaning together, and look at seasonal options, look for bottlenecks, look for sailing durations, realize how much time was spent waiting, look at annual round trips if we're looking at them. And I have brought one example to show how this is applied, looking at the Egyptian grain shipments to Rome. I won't dwell too long on this as we're nearing the end of the presentation, but I will jump into a few of the slides. This is for the month of April. Green arrows are not actually the routes, possible routes sailed. They're schematic of links, but they indicate links with good mobility, a high mobility, above 40%. Yellow shows a poor to fair mobility, and red would show very poor mobility. So in April, we can see that ships leaving from Alexandria can choose to go to Crete or to Cyrenaica. They can go via the Gulf of Sidra, west of Sicily, or they can go through Messina or via Malta. All options are open. The north option, the central option, and the southern coast option are all options. The dotted lines, the dots here indicate the mobility of coastal sailing, which is something else we measured, which is good on this coast and also fairly good on the northern coast of Anatolia, the southern coast of Anatolia. May, suddenly we see reduced mobility because the prevailing winds are beginning to set in. So I'll jump ahead to July. And in July, we see now we have prevailing winds, the typical summer prevailing winds, the Meltemi or the Etesian coming out of the Aegean, and the prevailing winds coming down the Adriatic or from the western Mediterranean. Coastal sailing along the shore of North Africa is impossible in July, and direct sailing also not possible. So the only things that was left for ships in the month of July and August and partial part of June is to sail northeast to the Antalya coast, reaching Cape Gelidonia and that area, and then to coastal sail towards Rhodes or Knudos, and then come carefully down through Carpathos to Crete. From Crete, it's possible to continue, or from Cyrenaica to reach Cyrenaica, which also has to come via the north coast. It's then possible to continue. Messina is closed in these months. It's not, there were too much contrary wind coming out of Messina. September starts to clear up, and October shows good mobility again directly westward from Alexandria, with a lot of open choices and quick sailing. And all this can be summarized into a chart which shows the olive color shows waiting time for each month of the year, January, February, March, April. We can see in the summer months of June, July, August, and September, there's a lot of waiting time, and sailing time is also very slow, 40 days sailing. But that's because of the coastal sailing needed from Cape Gelidonia towards Rhodes and perhaps on the south coast of Crete. So we can see in the summer, it's almost 70 days to reach Rome. And in the transitional periods, April, May, it's less than 30. October, November, also less than 30 days. So here we can see how practical it is to evaluate a historic context with the mobility measurements that the method has produced. And then we come to the final thing of predicting favorable winds. And I'll show two passages here. The one on the right is sailing from Paphos to Dor in the month of May 2005 in this case. It seemed to be all passages are almost direct, some of them a bit longer. but there are a few passages which were not feasible because of high seas and waves and wind, which would probably not be a good time to sail. So here, mostly good sailings, perhaps a few bad sailings. The same month, going the opposite direction from Dor to Paphos is quite difficult. Mostly unfavorable winds and very difficult sailing, and perhaps a few tracks indicating a good sailing. So when we come into, if we say, could this be predicted? We have to say the ancient mariner, could he predict when to sail and exploit a window? So we found that by machine learning and giving the weather at the departure, 3 days of weather at his point of departure, he was able to observable weather. Could he predict sailing this path? And we came to about 80 to 90%. It was capable of predicting a good passage. Unfortunately, he couldn't predict the bad passage very well, only about 75%. And the same in the other direction. Even though the majority are bad, he'd probably miss the 1 or 2 good opportunities. So we need to do more wind on this, and especially the issue of could he predict when not to sail, because the cost of making a mistake here could be drowning, whereas the cost here is only lost mobility. So we hope to investigate this further and perhaps come up with better machine learning models and be able to be accurate. And then we can see there are differences on different passages. So we will be able eventually to add an additional factor to the measurement of sailing mobility, is whether there's the capability of predicting. Because we say if the capability is low, they were prudent mariners. He wouldn't take the risk. They wouldn't take the risk. And that needs to be part of our overall calculation of mobility. So that's in the future. To summarize, in deriving potential sailing mobility, the ships, the mariners, and the wind, all three of them, are complexly intertwined, but they can be modeled. And the more we do case studies, we find that the mappings of potential sailing mobility can contribute, and they are contributing, to understandings on how maritime links were conducted. And on that note, I'd like to say thank you to my 2 supervisors, Debbie Zwickel and Adas Saroni, and a special thanks to the crew and volunteers of the replica ship. And thank you all for coming to this webinar and listening to me rabble on for 50 minutes. Thank you. Athena, please take the microphone. There we go.
Thank you very much, David. I really enjoyed hearing about your research in more depth, and that was a very clear presentation for me to follow. And we definitely have some questions that are coming your way. So do remember that you can type your questions as we're going along in the question and answer pane in the chat, and I'll try and follow those up as best I can. The first question, David, is Joe Machin wanted to find out about the type of software you're using to model the sailings and journey durations and weather. So
we're using a regatta software. It's called QTVLM. It's available on the shelf. The reason we chose this one is, first of all, it's a fairly a good program, but we can run it in batch mode, because there was no way that we could do 1.2 or 1.5 million simulated sailings and manually set up each one. So it's batch, but it's regatta weather routing software. The weather we used for it is we took from the reanalysis database of ERA5 wind and other weather data it's a 27-kilometer resolution and temporal resolution of 1 hour. We also took at 2.5-kilometer resolution sea currents, surface currents. So The simulation included both wind and currents, and that modeled the ship sailing. Now the simulator conducted sailings in all conditions. It has no fear, it's never hungry, it's never thirsty, it knows exactly where it is, so it could complete all the things. The introduction or the modeling of the mariner was basically by looking at the outcomes using criteria and dividing it into the set of reasonable and the set of unreasonable passages. Thank you.
Okay, I hope that answered your question, Joe. And we have another question by Ben Effer. He writes that it seems predictable when trade ships would follow certain routes, given that waiting was a norm during unfavorable winds. And would pirates use this knowledge to their favor?
Can you repeat that, please?
It seems that it's predictable when trade ships would follow certain routes, and so they would know that they'd have to wait at certain points in times, wait out the unfavorable winds. So would pirates also use this knowledge to their advantage?
I've thought about that, and we discussed it in Malta at the presentation. There was on pirates and where they chose to be. And the Cilician coast, Cilician coast definitely is very difficult in the summertime to sail westward there. And ships sailing westward would have to do daily runs using the breeze, which sometimes they'd get and sometimes they wouldn't be. So they'd be hanging out in coves there, in anchorages, for long periods of time, or relatively long periods. So the pirates' prey would definitely focus in that area. So definitely the observing the mobility and understanding the mobility and where coastal sailing is, you're going to be forced to do coastal sailing, definitely would attract pirates. An open passage in blue water away from the coast the pirates would have very little likelihood of intercepting a ship.
That's interesting, because the area exactly that you're describing, of course, was known for its piracy. It was one of the things that when the Romans moved into the Eastern Mediterranean, they wanted to quell, was this, especially in that area. That's interesting to follow up for sure. I hope that answers your question, Ben. Yes, great. And we have also another question from Tim Vesky, who's asking about there, of course, has been a change in climate during the last decades. Would it not have been better to make use of older data, perhaps collected before 1980? And he continues on, I know from personal experience, so heavy traditional cruising yacht of 20 tons displacement, that in the Mediterranean, even a wind of force 3 to 4 will create a short seaway quickly. It is not unusual that the wind will abate and start to blow with less strength from a different direction. As the result, the boat will pitch and roll, spilling the wind from the sails, and thus makes very little headway. Did you consider this in your calculation about the VGM? So 2 questions there, using earlier data, pre-1980 data, and then also...
2 questions.
Yeah.
First of all, we rely on a climatological study showing that there's been no change in general in climate in the Mediterranean. Now, statistically, looking at recent year fluctuations that we sometimes have, not so much in the wind patterns, but more in temperature, humidity, and in precipitation is where the differences occur. 30 years of data would have been better than 15 years, because 30 years statistically will cover short-term, or what they call decadal climatological fluctuations. But the best wind data that we can get is only about 15 years old, 15 to 20 years old. Everything previously, wind data was only what was reported from ships, except from coastal stations. So anything away from the shore was only ships reporting right up until 1974. From 74, the other sensors came into play. And the last 30 years or 20 years, satellite data gives excellent wind information. So and we decided not to go before 2004 because the best and the reanalysis databases with wind begin in about 2004. The wind data is more reliable. So we definitely considered that point, but found that actually the recent data is better than data from 30 or 40 years ago. The simulator takes into account the fluctuations of the wind. We didn't model the waves. So the oscillation of the ship and losing some efficiency because of the waves was not added, although the simulator has the facility to factor the possible difference in waves if we have wave data. But we do have wave data to decide when a passage was not reasonable to sail if waves were higher than 2.75 meters. So in other words, high waves will put our analysis into the bad group. So the height of waves is taken into account.
Height of waves is taken into account, and let's see. He also has this is the other question. I hope, Tim, that has answered your question about making headway with the boat pitching and rolling in the calculation about velocity made good. So I hope that has answered your question. Are there any other questions? I have, if not any immediate questions, I do have one actually thinking about seasonality, where we've always kind of blanket following on from text. Of course, you mentioned Casson early on there about this, the summer sailing season being blanketed as a good sailing season, and these kind of general statements from ancient authors. But I'm wondering if it can even be taken another step, where you have some shipwrecks now are beginning to, the organic material that's coming from these shipwrecks is really, really nice. And in some cases, we can start to see, I'm thinking about, it's not open sea, but a site, for example, like IJNA, where some of the shipwrecks had organics preserved, for example, containers that were cherries. And knowing that cherries and kind of this region come into harvest in early May and things, and I'm just wondering if that could be another step that you're thinking about, is kind of even taking the story of some of these shipwrecks further. If there's some that present themselves with really good organic cargo that can be specifically assigned a certain season, if that can help you even kind of give the story line of the shipwreck even more confidence, you could say, in your interpretation.
Definitely, and we've recently done that looking at the Ma'agan Mikhael II shipwreck. There was a lot of organic material there, including pollen that could be analyzed, and so there is a more or less accurate dating of when she sunk off the coast of Israel, which was late in the autumn. And then we looked at which possible routes she could have arrived on, based on that period of the year, and it can be definitely done in other occasions. Another thing that we do is I showed here 2 or 3 samples of the tracks, the actual routing tracks, optimal routing tracks, and we can see definitely in some cases, especially sailings from the Aegean to Rome, coming around the coasts of Sicily. In some cases, the winds are pushing the ships into interaction or close interaction with the coast, and definitely you can see which months of the year would have been supplying more shipwrecks on a particular coast, and on which coasts and which point on the coast would be worthwhile looking for shipwrecks. Okay.
Let's see if we have any more questions for David here. If anyone has any questions, now's the time to ask. And Peter, do you have anything to add? Or I see a note here that you would like to answer this question, but I don't know.
No, that's
If that
fine.
means
I
that's
just
the
wanted to say
system.
thank you very much. That's the technical system working behind the scenes. Thank you very much, David. It was an excellent presentation, brought back some memories of my sailing days, and very stimulating questions. Also interesting to bring in climate change there, of course. I have put the chat in the chat. I've put the link to the open access article that David has written. And I do believe that we've just got another question.
Yeah,
so
certainly.
I'll take you to Athena for that.
Sure. Okay. Ray Dixon asks, does your modeling show how many trade routes would be reciprocal, backward and forward, against how many would require multiple ports and trade routes to follow the winds?
Okay, excellent question. I showed in examining the grain from Alexandria to Rhodes how difficult it is to exit the Eastern Mediterranean because of the Atessian winds, 5 months of the year, very poor capabilities. And we did an examination of, okay, what could ships do during those 5 months in the Eastern Mediterranean? And we took all routes in the Eastern Mediterranean that were measured, all passages, and then filtered it, showing which of them could have been sailed bidirectionally with good mobility. And it immediately showed 3 sets of tracks that could definitely be trade routes between the Western Delta in Egypt and Western Cyprus and the Lycian coast, the Eastern Delta with the Southern Levant and Eastern Cyprus, and then the Cilician coast. I keep mixing up. The east of Cyprus to the north, to the southern shore of Asia Minor. So it definitely shows up that there could have been a lot of sailing, a beam to the wind. In other words, across the prevailing winds, and it could be definitely two-way passages and with excellent mobility in both directions. So while it's very difficult to exit the Eastern Mediterranean, if you stay within those networks, you can go backwards and forth the whole summer.
Thank you very much. I think that's all of the questions that have come through now. But if anything does occur to you later on, you can always contact the Nautical Archaeology Society and we will pass on to the experts to answer the questions. So it just leaves me to thank David for his presentation and Athena for managing the whole event and sharing the questions. Thank you very much to everyone who's attended. A big thank you to Honor Frost Foundation for making this possible. And on behalf of the Nautical Archaeology Society and our presenters, thank you very much for joining us today and enjoy the rest of your day, afternoon or evening, wherever you are in the world.
Thank you.
Thank you, David. Thank you, everyone. Thank you, Peter.
Thank you.
Thank you.
Bye.
Bye-bye.